Hi, my name is Enoch Wang, and welcome to the 28th and hopefully the last recording of this presentation, Juicing V8, a primary account for the forensics of the V8 JavaScript engine. My colleagues include Samuel Zurowski, Orion Duffy, and Tyler Thomas, the original proposal writer for this project. Our PI is Ibrahim Baggili. He is the founder and director of the University of New Haven Cyber Forensics and Research and Education Group. His work is commonly supported by the NSA and MITRE, and he is a personal mentor of mine. This work is sponsored by CAE and the National Security Agency. I'll be breaking down this presentation into 6 different sections. First with the introduction, discussing V8, a little bit about V8, how it works, and the motivations and goals, our initial research, findings, methodology, discussion, and the evaluation of our tool. Then I'll finally end with the conclusion and a bit of discussion on the future work of this project. Excuse me. So, what is V8? So, V8 is an open source interpreter created by Google to enable JavaScript within browsers. It's primarily created to run JavaScript on browsers in an optimized manner by handling the stack, memory heap, garbage collection, and objects. It's written in C++, so it's pretty fast, and it's constantly being optimized, so it does change. That does come into factor later. Because it's so efficient, it's not just used in Chrome and Chromium browsers such as Brave and Opera, but it's also used in applications such as Discord and Node.js. The primary motivation for this work is Tyler's previous publication, which is the Memory Foreshadow, where he explored the memory forensics of crypto wallets. These crypto wallets, many of them ran on Electrum, which runs on V8. He was not able to extract more objects from them because they were stored within a V8 data structure type. But if we're able to create a plugin that's able to extract V8 data structures, then we would not only be able to apply this on crypto wallets, but browsers as well, anything that runs on V8. So, this would allow investigators to basically get more bang for their buck when they analyze live memory. The final piece was Ali Gombe's Droid Scraper, which paved the way by leveraging the mechanics of garbage collection to extract objects. This kind of showed us that it was kind of possible to do this, so we decided to go along and create this research. So the goals of our research include first reverse engineering V8 to understand how it works. Then we wanted to identify the data structures, find V8 objects in live memory, and then create a tool in Volatility that was capable of extracting these objects consistently. And finally, evaluate the tool to see, how it held up. So in reverse engineering V8, first we started with the code, but it's open source, so that was nice. We could just read it directly. From the open source code, we were able to determine 3 main things. First, that everything interesting is stored within something called the V8 isolate. Second, there are things called object maps, which contain information about the object, descriptive information, kind of like what kind of object it is, if it's a string or an integer, how many objects there are, what is the size, useful information such as property information. And then there is the MetaMap. The MetaMap is a root map that is referenced by all object maps. It references its own address and its data structure, which comes up later, and is identifiable by its magic bytes, which are FF03, 20, or 40. So the other aspect of reverse engineering V8 was using something called LL Node. LL Node is a Node.js debugging tool. It basically breaks down high-level data types into low-level primitives. It's using something called the compile leak execute. It's basically used by developers to create a live instance of LL Node and experiment with that to really understand how V8 works. That's basically what we used it for, but we used it to analyze the memory structure to determine if the relationship between data types were as we previously described. We verified these findings with something called Cheat Engine, which reads live process memory and volatility by taking a snapshot of that same image and reading it manually through Volatility. So yeah, it's similar to NSA's Ghidra, except NSA Ghidra works off breaking down binaries to try to determine what they do, while we're creating a live instance and kind of experimenting and poking and prodding at that. So here's a figure explaining the data structure I described before. Basically, on the left, we have an object. Within the object, we have a pointer to its map, some properties and data if you want that afterwards, which you probably do. And then a pointer goes to the address of the object map. Within the first instance of the object map, you have a MetaMap pointer. And then in the second field, you have information such as instance type, instance size, instance slack, and you have descriptors that will help you understand what the object is. So if you were to look at this in live memory of what it actually looks like, it looks something like this. Whereas you have you first have the object structure. This is the object structure, and the first instance, as you can see, you have a pointer to the address of its object map. They may not look the same, but that's because you have to reverse the Indianness of this object. Sorry, you have to reverse the Indianness of this pointer. Trust me, I've done it a million times. It goes to this address, but you will notice that if you were to reverse the Indian, there's a 1 here and there's not a 1 here. That's because to align the data structures properly, you have to subtract 1. That follows consistently when you want to find the MetaMap from the object map. So this pointer goes to this address. And then finally, you can see how this pointer points to its own address, which is useful. So the final aspect of reverse engineering V8 is garbage collection. We wanted to understand how garbage collection worked because we wanted to understand what kind of objects we could potentially extract, what more objects we can extract that, like a snapshot analyzer could not find, and what is the effect of garbage collection on memory forensics as a whole. So first, understanding how garbage collection works in V8. Which this is important because part of the reason why V8 is so useful is because it converted stop the world execution to a combination of concurrent and parallel, which is the idea of instead of stopping your JavaScript from running, you have some of it run and some of it pause so you can clean up some of it in the background. This allows you to seamlessly watch videos so your video doesn't like stutter. Which is very useful. It does this through something called the weak generational hypothesis, which is the idea that most objects that are created will be destroyed within very, very quickly. So it's the idea that 98% of objects die quickly. To leverage this, V8 creates something called the young generation and the old generation, where young generation contains new objects, which are often cleaned up and promoted, and old generation, which have objects that survived garbage collection, and those last 2% of objects live and are probably going to be there for a while. So yeah. To find objects, garbage collection does something called root object tracing, which is finding references of the object within the execution of the application of JavaScript. So it's trying to find where in execution if this object will ever be referenced again. If not, if nothing ever references the object, you obtain something called transitive closure. It decides it's dead, boom, it gets cleaned up. So on the left, you can kind of see a graph of what this looks like in memory. So if you see, first you have your application starts running, you create a lot of objects, new user objects, and instantly they're no longer useful and they're all gone. So you have something called a minor collection and then a major collection. So after maybe around 98% of the objects are dead, you have major collections, and what's left is likely to just keep surviving. So then these objects you can promote to something called the old generation space. So you basically have 2 bins. The first bin, sorry, the first bin is to kind of collect new generation that gets swapped out all the time. You're assuming 98% of these are just going to be swept away instantly, and then you keep 2% of it to store somewhere else as kind of like reference. So on the right we have a bit of a diagram to show how this works. So in 3 different objects. So the first object, let's say the object is alive, it stays alive, and then it undergoes garbage collection once in the scavenge process, and then it stays there because it survived one iteration of garbage collection. Good job. The second object, it survives again. Let's say that same object goes through garbage collection again twice, and then it becomes promoted. Then it gets moved. So copy operations are expensive. So to reduce the amount of copy operations, you only do this to those 2% of objects that keep surviving. So it gets promoted to the old data space, and then in this old data space, these objects do get cleaned up eventually, but they stay here for a very long time, as you can see in this graph. And then the third type of object is just, it was there, it was created, it's no longer there, you clean it up, it's gone. So our methodology. So as mentioned before, some key aspects was that the MetaMap could be found by referencing its own map, right? So within its data structure, the map contains a pointer to its own map. So what we did was we created an algorithm. We created a volatility plugin that uses Yara scans to look for first a series of magic bytes. These magic bytes gives us a series of data structures, and then we analyze these data structures to find the MetaMap. We validate it's the MetaMap by finding if the data structure references its own address. If it does this, we know it's the MetaMap. That's great. So now we have the MetaMap. So the first part, find the MetaMap using the magic bytes, and then validate it's the MetaMap. Then we want to find every object map by finding every single reference of the MetaMap within process memory. Okay, so now we have a list of object maps. As you can see, this could get out of hand very quickly. And then finally, we take that list of object maps and find every reference of every object, every reference of that object map, which will give us every single object. Okay, so not the most optimized algorithm in the world, I'll admit. It does take some time to run this plugin, and it also executes in Python, which is not the fastest programming language in the world. But hopefully in the future, there may be room for improvement. We may convert this to C++. But yeah, in its current state, some objects take a very long time to extract. But fortunately, it works. So that's the good thing. If you have unlimited processing power and unlimited time, this plugin works, which is great. So this is kind of like a sample output of our early iterations of it. First, it tries to find the Node.js process ID. Then you find the opcode address where the magic bytes are found. It walks the pointers, finds the MetaMap. From that MetaMap, it finds the object map, and then finally you extract the object and spit out its properties. So how do we make that better? Because that junk before, probably not useful for an investigator. So first we kind of want to identify all the different kinds of types, right? There are different kinds of object types, and you have different kinds of maps, right? So first you have something called an internalized string type, which is 0, 0. Then you have one byte internalized string type 0, 8. And then you have all these different other types, right? So something to really understand with how V8 works, almost every single one of these types contain objects that are internally handling. Means it's kind of background stuff that the user has nothing to do with. Almost all the user objects are stored within the 1 byte internalized string type, which is the 0x8 type. 0x8 type. You can basically specify this type and get every single thing that the user wrote or whatever the user created, right? So for the most part, investigators are only really going to be interested in the 0x8 type. But still, we wanted to add as many functionalities to this plugin as possible. So first, we enabled the user to extract the object properties if they want from the object map, and then the object data, which of course contains all that juicy information that you might find, like the wallet address or whatever password that you need to break whatever encryption. And then the number of objects if you want to print those, just to kind of get a head count of how many objects you're really looking at. Then we wanted to add support for different versions of Node.js, which we did. And then we wanted to test support for other applications, including Discord and Chrome. So I'll go into Discord and Chrome later, but let's continue for now. So we wanted to evaluate how good our application was at extracting objects. So we used the Chrome's heap dump tool, which basically takes a heap snapshot and reads how many objects it can find within its heap snapshot. Everyone who has Chrome has this. It's in the developer tools, and it basically shows you what's going on in the background for V8. So on the left in the heap count, this is basically how many objects Chrome was able to identify from this. But in theory, because some of these objects are potentially dead and not cleaned up by the garbage collector, we could find more. And if you can see on the right, which is our plugin count, that is typically the case. In some cases, we find a little less, maybe because our plugin is not completely done. Maybe we don't have support for those data types. There may be a number of reasons for this, but for the most part, we're able to extract everything that Chrome is able to identify. But for specific types like the array and array buffer, we're able to find much more than what Chrome is able to identify. 1,000 objects more, over 1,000 objects more, right? So this is interesting, and this makes sense because there is a small window, if you understand how garbage collection works, in which objects can exist and are dead, which Chrome doesn't consider an object anymore, but are still in memory. So to try to kind of prove that there is a relationship between the number of objects that a user creates and the number of objects our plugin is able to extract, we took snapshots of a application running a custom Node.js application that creates objects, and we take a snapshot each time we add an object. So every time we add an object, we take a snapshot. Every time we add an object, we take a snapshot. Every time we add an object, we take a snapshot. And we see how many objects we're able to extract. And as you can see for the 0x8 type, there's a direct correlation as to, obviously if you create more objects, you're going to find more of it within, memory. So that's great. We found this direct correlation. However, very keen viewers are going to notice that I omitted 1 and 7. And this is not to lie to you. Also, you might notice that it starts from 6040 to 6070. So you can just see kind of like the increment of objects, but that is not really relevant. The issue is why I omitted 1 and 7 is because if you were to add them to the graph, they would not even be on the scale of the graph. It would make this relationship seem insignificant. And if we move to the 0x421, which is a internalized type, it's an object type that really isn't related to how many user objects are created. In 1 and 7, there are significantly less amount of objects extracted. Now, what we can infer here is probably garbage collection is being, is occurring. So it does affect the amount of objects you can extract. So keep in mind for investigators that try not to execute garbage collection. As you can see, only 2 out of 10 of the iterations garbage collection has not occurred, but it does occur. So and as you can see, it eliminates almost half of the objects that we are able to extract. So for investigators, garbage collection does affect memory forensics, and it's pretty severe. So more work can be done into this research to identify exactly how bad it is and how we can try to stop garbage collection from occurring when you want to try to collect a clean image. But yeah, that's to be seen in the future. Finally, we wanted to kind of bring this full circle to what Tyler originally wanted to do by creating a case study. So in this case study I basically just had a small crypto miner running and I took a snapshot of it, and then I ran it through our plugin. And through our plugin and extracting the 0x8 type, we were able to see that we're able to get the pool that it was mining on, the wallet address it was mining to, and the password, which is just, it's not really a password, it's just kind of like a keyword that you add to it to try to help identify what, just what you're mining to. So yeah, so this could be useful for an investigator if they want to analyze a piece of memory, a piece of malware or something, and see that if it's running a crypto miner, you can find the address that's mining to, and from that maybe you can track the perpetrator. So yeah. So finally, the conclusion. We're here. So first, we mapped out and verified the layout of V8 data structures. We determined that it's possible to extract these V8 data structures through carving these data structures. Then we created a plugin called the V8 Map Scan, which I did not mention before, and it supports all versions of Node. Then we talking on some of the future work, we determined that it's possible to achieve support for Chrome, but this will require finding a way to identify the V8 isolate from multiple processes and subprocesses. If you ever open up Task Manager while running Chrome, you'll notice it has many processes. Each one of these processes has memory, and we have to go through every single one to identify the correct V8 isolate. Each one has a V8 isolate, but not all of them are the core V8 isolate that contains the heap and all the important information where you will find this. So there needs to be a new way, maybe a new set of magic bytes, which we haven't determined yet, to identify this core isolate. Otherwise, you just need a lot of processing power if you want to use this on Chrome, because you'll have to run multiple instances of this plugin. So then the final aspect is achieving support for Discord, which was done by one of our colleagues named Matthew Piscacelli. He created a 32-bit version of this plugin. For some reason, Discord runs on 32-bit and does not run on 64-bit. The plugin runs on 64-bit. So by converting many aspects of the plugin to 32-bit, he was able to extract some data structures, but not extract the objects because the plugin is not done yet. So that will require a little bit of more work, but it can easily get done. And finally, we need to consider whether or not we want to upgrade this version of the plugin for Volatility 3, as it uses a completely different format. Instead of walking the eProcess structure to identify things within memory, it uses something called the intermediate symbol format. So this will have to change the whole way we create this plugin. All right, thanks for listening. I'd like to thank Matthew Piscacelli for creating the Discord version of this plugin, and Haley Johnson for being the overall program manager for this project. Please feel free to ask questions. I believe I'll be here when this is presenting. If not, all questions will go to my email. Thank you.